Thank you for attending today's SBCA webinar, Understanding Truss Design Drawings, Part 1. This is the 8th in a series of webinars aimed at informing building designers, whether they're architects, engineers, or others in the design community, on aspects of the component manufacturing industry. The goal of this series is to provide structural component design guidance, as well as provide perspectives on what today's component manufacturing industry is capable of, and explore how our industry can be an effective partner with building designers in ways that will make their lives easier and/or make them heroes in the eyes of their customers. In this presentation, we're going to start a deep dive into Truss Design Drawings, or TDDs, which is an essential design document in the construction of a building. Now, because the audience for any one of these presentations may include design professionals from different disciplines with varying levels of experience, who work primarily on projects ranging from single family to multifamily to light commercial, most of my observations will remain at the 30,000-foot view. My name is Sean Shields. I'm the Director of Marketing for the Structural Building Components Association, SBCA. I've been with the association for a little over 20 years now, and will be bringing to bear my experience talking with component manufacturers across the United States throughout this presentation. I want to give you just a brief summary of what we'll cover in this presentation. I will start by providing a brief overview of SBCA and its role in the component manufacturing industry. I do this because I want to give you a sense for the size of the component manufacturing industry, as well as the role of SBCA in that industry. If you've attended one of these webinars before, or you are a member of SBCA, I apologize. It will be redundant information that you probably already know, but for all the building designers who may be attending this or exposed to this for the first time, this will be important information for them to know. I'll then spend a few minutes giving a high-level overview of the truss design process to understand where the truss design drawing fits in. And then I'll spend a majority of this presentation walking through the top fields and the graphical elements of the truss design drawing. Finally, I will end with a discussion on how today's component manufacturer can be a valuable resource to building designers in the building design process. So SBCA is a trade association for the structural building components industry. It's the premier trade association in North America. With over 40 years of history, SBCA has developed an extensive network that enables it to reach the entire length and breadth of this unique industry. SBCA has a strong tradition of providing sound engineering and fabrication guidance to its members to promote their growth and success in the marketplace. But as that market has matured, SBCA's primary focus has shifted recently to helping build connections between companies and individuals throughout the industry, whether they're in the same local market or spread across the continent. These relationships are built through both face-to-face events, virtual events, online, and digital communication. SBCA's premier face-to-face event is the annual Building Component Manufacturers Conference, or BCMC. This is traditionally held in the fall. BCMC brings together thousands of manufacturers and suppliers together for a week of intense networking, idea sharing, and business transactions. BCMC is open to anyone and everyone who would like to attend. In addition to the BCMC show, SBCA hosts 3 additional face-to-face meetings throughout the year called Open Quarterly Meetings, or OQMs. These meetings are held across the country and offer anyone a more intimate opportunity to build relationships with some of the largest and most forward-thinking component manufacturers in the industry. Finally, SBCA has developed an extensive suite of tools and resources for today's manufacturer that range from digital quality management software to an extensive library of online training modules. To give you a sense for how large SBCA's membership is, this map is a scatter plot of the over 1,300 component manufacturing facilities located in the United States. Of those dots, 907 of them belong to SBCA member companies. As you can see, these facilities reach every community in the country. allowing builders to use these products in any project, no matter where that project is located. And to give you a sense of scale, SBCA member facilities sold approximately $9.12 billion in product in 2023 out of an estimated total of $9.31 billion. SBCA is an inclusive organization. We welcome anyone and everyone engaged in the light frame construction industry to get them tied into our extensive network of structural component manufacturers and their supply chain. There's an infinite number of opportunities for individuals to get involved, meet these manufacturers, share ideas, solve problems, receive and offer education, and most importantly, build meaningful business relationships that can transform the way anyone approaches their job and positively alter the trajectory of their business and career. Now, as we begin our discussion on truss design drawings, I do want to start with the codes and standards references that provide the basis for what is included in these important documents. A truss design drawing, or again, a TDD, is a document that provides a graphical representation of a singular truss and includes very specific information for structural engineers, building designers, and building officials to review. While the code requires building officials to review truss design drawings for approval prior to installation, as you see in the words on the screen, these documents must also be reviewed and approved by the building designer prior to their submittal to the building official. Section 2303.4.1.1 of the International Building Code, or IBC, lists the information that must be included in the truss design drawing for buildings constructed under the IBC code. In the International Residential Code, or IRC, Section 502.12.4 does the same thing. It contains a similar list of items that must be included at a minimum on the individual truss design drawings, again, for buildings constructed under the IRC. And I use the word similar because it's a different list of items. And in some cases, different words are used in the IRC to refer to the same data points that are listed in the IBC. Finally, I want to mention the standard that governs the design and manufacturing of metal plate connected wood trusses. ANSI TPI 1. This is a consensus-based standard that was first published by the Truss Plate Institute in 1961 and is updated on a regular basis. The most recent edition of ANSI TPI 1 is 2022, which was approved as an American national standard in December 2022. Now, the current version referenced in the model codes is currently ANSI TPI 1 2014, but the new standard will be incorporated into the 2027 model codes. Chapter 2 of the ANSI TPI 1 standard outlines the information required on truss design drawings. What you have is essentially 3 separate lists in 3 separate documents on what should be included on the truss design drawings. As part of the incorporation of TPI 1 into the 2027 model codes, there is currently an effort underway by the Truss Plate Institute, SBCA, and the National Council of Structural Engineers Association, or NCSEA, to amend the model codes to harmonize the TDD requirements of the IBC and IRC to be harmonious with what is found in the TPI 1 standard. Now, the main motivation for this, besides providing consistency, is a recognition that the TPI 1 standard is updated on a different schedule than the building code is. But since TPI 1 reflects the most recent understanding of truss performance in the field, it should be the source that all others reference when it comes to truss designs, and specifically what is included on a truss design drawing. All that being said, despite the current differences between the different model codes and the TPI 1 standard, TDDs have a relatively standardized layout, and that is what we will start exploring today. Now, trusses are singular structural framing elements. And they've been around since the 1950s, when the first metal connector plate that didn't require any additional fasteners was invented by J. Calvin Jurian. As trusses gained in popularity, the motivation increased to find a more efficient way to design individual trusses that didn't involve hours of hand calculations and paper and pencil. In the early 1970s, the first truss design software was developed that allowed manufacturers to automate certain aspects of the truss design process. Pictured here is Bill Rousseau, one of the earliest software pioneers in the component manufacturing industry. When you think about the 1970s, and the adoption of computers within the component manufacturing industry, it points out that these manufacturers were some of the first entities in the residential construction industry to adopt personal computers in the office space in order to have access to this software. Over the next 5 decades, many companies developed software solutions that provided varying levels of assistance to component manufacturers in the design of trusses. While metal connector plates were typically their primary product, increasingly it was difficult for a plate manufacturer to compete in the marketplace if they didn't interface well with a good truss design software. Now, over the years, those who didn't have superior software found themselves either going out of business or were purchased by those who did. And so today, we really only have 4 companies that remain that supply truss design software and connector plates to this $9 billion industry. And as you can see on the screen, that's MyTech, which is a Berkshire Hathaway company, Alpine, which is an ITW company, Simpson Strong-Tie, and Eagle Metal Products. Every component manufacturer in the United States uses one of these 4 proprietary design software suites to develop individual truss designs. And I bring this up and highlight it because, again, while truss design drawings are largely standardized, each software platform does organize the TDD output from their software a little bit differently. So if you're a building designer or building official who needs to review these things, that's one of the reasons why you'll see subtle differences from one set of truss design drawings to another. Now, before I move on to sort of a quick summary of the truss design process itself, I just want to note that the 4 companies that provide truss design software have also been investing heavily into the integration of other software platforms in recent years, increasing the power and capabilities of this proprietary software that they supply to component manufacturers. And this includes software that can integrate plan reading and building design. It can enable 3D modeling and interface with building information modeling platforms. In addition to more robust component design capabilities, the software now seamlessly integrates with computerized production equipment as well, which adds to precision and quality. And multiple companies have even began exploring ways to incorporate artificial intelligence into aspects of the design process through these software platforms. All of these digital tools help leverage the expertise and knowledge that component manufacturers already have, so that they can be effective and valuable partners to today's building designers, builders, and the rest of their customer base. I'm going to spend just a couple of minutes talking about the truss design process to set the stage for how building designers fit into this process and ultimately highlight how building designers can help improve the process. As you can see on the screen, I'm going to incorporate a few short video clips, and I want to emphasize short video clips of truss designers in action. This is a slight upgrade from static photos in that they give you a sense for what the truss designers and truss technicians in the industry do on a daily basis. Now, with over 1,300 manufacturing locations across the US, it shouldn't be surprising that the overall truss design process can vary greatly from the East Coast to the West Coast and everywhere in between. As a consequence, I'm going to talk in general terms about the truss design process. If you or your market handle this process slightly differently, that just sort of proves my point. Now, typically in the initial project bid phase, the component manufacturer goes through an estimation process that generates their quote for a truss package. That estimation process typically involves going through the proposed building plans and identifying key elements of the truss package, as well as making assumptions regarding any missing data in the building plans. Once that bid is accepted and turned into an order, the component manufacturer will take a deep dive into the building plans and submit RFIs or requests for information to the building designer or the equivalent to clarify vague language or obtain missing information. During this phase, the component manufacturer may also identify value engineering opportunities, essentially areas where specifications could be changed to provide a greater material efficiency or to reduce overall construction costs, sometimes to deal with supply chain constraints or labor issues. There's lots of different motivations for some of these value engineering options, but every component manufacturer typically engages in this process. Now, while this is the way things by and large work, hopefully it's clear that the earlier the component manufacturer gets involved in the building design process, the more value they can bring to the building designer in the form of advice or verification of whether a particular design element is possible or fits well within a project's budget. The earlier these questions can be answered and the value engineering opportunities can be brought up and addressed, obviously the more impactful they can be from a cost and time perspective. Another way to think about this is the component manufacturer is the bridge between the concepts that the building designer is coming up with and what is actually built in the field. And they do this day in and day out, which provides a lot of experience to draw from. So while the overall roof, wall, and floor profiles are dictated by the architect, so the shape of the box, and the loading conditions are determined by the engineer when necessary, the component manufacturer and truss designer have a great deal of latitude through the software to decide how to arrange web patterns to arrive at an optimal structural framing solution. Now, sometimes that solution is very straightforward, but as you'll see in some of the profiles that we'll look at in this presentation, the solution sometimes is anything but intuitive. And occasionally, the truss designer will determine that a truss simply isn't possible given the initial design criteria. In those cases, the manufacturer will typically go back to the customer or building designer to suggest alternatives, such as spacing trusses closer together, or like, let's say in the case of floor trusses, increasing the floor truss depth. The point is that with today's robust design software that we just talked about, the options available to a building designer are virtually limitless, as long as they are pursued with the component manufacturer prior to the start of construction. The last thing I want to say on this is that during the individual truss design process, the trusses are laid out and are shown graphically in a truss placement diagram. This diagram includes important information also provided on individual truss design drawings and is a helpful document to building designers, building officials, and installers to understand where each individual truss is designed to be placed within the overall roof or floor system. The reason why I bring this up is because truss placement diagrams are often talked about in the same sentence as truss design drawings. They're both aspects of the truss submittal package. But I want to make the point that the truss placement diagram is not an engineered document. It is merely a graphical representation of the information contained in the individual truss design drawings. So while truss design drawings can be and regularly are reviewed and sealed by a registered design professional, that is not the intention of a truss placement diagram. Okay, truss design drawings. Now, while the information on a truss design drawing is by and large the same, no matter which proprietary design software package the manufacturer uses, as I mentioned earlier, the layout of the truss design drawing will vary slightly. In part one of this presentation, I'm going to focus primarily on the information contained in the top half or graphical portion of the truss design drawing. And I'll walk through some of the minor differences that we might see between different TDDs. And then in part two of this series, we'll wade through the rest of the information in the truss design drawing and discuss what may be most important to focus on when reviewing each truss design drawing in the truss submittal package. Okay, so the first piece of information on the truss design drawing, located in the top left corner typically, is the job number. This is primarily an internal identifier for which job the truss is a part of. The customer and/or building designer can reference this number when reviewing the truss submittal package in case there are questions or concerns. This number can also help the manufacturer quickly identify all the other trusses in the same roof or floor system. I should note that there isn't a standardized process for job numbers. Each component manufacturer typically has their own internal process for assigning this value. So there typically isn't meaning behind this number. Again, each truss in a floor or roof system is designed as a single structural element. Once all of the trusses in a structural system are individually designed to resist the expected load conditions provided by the building designer, all of the trusses in the system are graphically labeled on a truss placement diagram. The truss placement diagram shows where each truss is located within the system. For ease of identification within that system, each truss is given a unique ID tag. Now, these tags may be duplicated if the same truss design is used multiple times within the same system. For instance, as you can see on the screen, if all the plies in a multi-ply girder may have the same tag like G1_ply, or a series of identical trusses over a garage may all have the same tag T1. Some component manufacturers may choose to add or incorporate additional information into this tag. For instance, like the building code that's used, the type of the truss, or any other designation pertinent to the system design. Again, the reason why this truss tag is used is it's to help quickly locate where this particular individual truss may be found within the overall roof or floor system on the truss placement diagram. Again, just like with the job number, the truss tag can also be used effectively by the building designer or the building official to quickly identify a particular truss that may have an issue. Now, the quantity field will identify whether there is more than one of a particular truss design with the assigned truss tag in a system. This is useful information for everyone from the building designer during the review process to the production line workers to the framers in the field, so they know how many of a given truss are in a particular truss package. Now, in the field, framers would typically find all of the trusses within a particular ID tag stacked on top of each other in a truss bundle. As you can see on the screen, this is an example of one truss bundle. These are stacked, similar trusses are stacked on top of each other and banded together because of the manufacturing process itself. Trusses with the same design will be fabricated typically consecutively because it minimizes the number of physical setups on the assembly table for a particular job. It also has the added benefit that trusses with the same profile are easier to band together to provide stability during the transport to the job site. Next, let's look at the pieces or ply section of the TDD. It's important to differentiate this field from the quantity field that we just talked about. The quantity field indicates how many trusses in a system with a particular truss ID tag there are. In most instances, the ply or pieces field would then be just 1. But for multiply girders or multiply trusses, you will typically see a 1 in the quantity field, and then the numbers 2 through 5 in the pieces or ply field. Now, different parts of the country handle multiply girders or multiply girder trusses or multiply trusses differently. In some parts of the country, like in the Midwest, the multiple plies will be fastened together in the manufacturing facility and shipped to the job site as one assembly. But in other parts of the country, like in the South, the plies will typically be shipped separately and will need to be fastened together in the field. One possible reason for this regional difference is weight. A pre-assembled multiply girder weighs a lot, and typically a crane or at least a piece of heavy equipment will be needed on the job site to hoist a multiply truss into place. Cranes are more commonly used in places like the Midwest than in the South. But that isn't a hard and fast rule. There are certainly component manufacturers and framers in the Midwest and South that do the exact opposite. It's typically the preference of the manufacturer's customer that dictates what's done. But again, the component manufacturer will typically do whatever the customer or the market dictates, whether they pre-assemble the multiply trusses or have them assembled in a field. At first glance, the date portion of the TDD on this particular truss design drawing, that date is a very small field. Sometimes it's much more prominent on other truss design drawings. The date field may seem a little straightforward, but there are many different ways in which this field could be used by the component manufacturer. Some manufacturers may only list the date the truss was originally designed. Other manufacturers may include both the date the truss was designed and also the date the truss was manufactured. Others may also include the delivery date of the truss in this field, or even the latest revision date, if applicable. In this instance, you can't see it very well, but 2 dates are listed. The first date indicates when the latest version of the truss design drawing was completed, while the second date lists when the truss design drawing was last printed to a PDF file. Again, there are really no hard and fast requirements on how the date field should be used. So if there ever is any question on what the dates are that are listed, it's best to communicate directly with the manufacturer. Okay, so let's get into the graphical portion of the truss design drawing. All the measurements on the truss design drawing are listed as 3 separate numbers. So you can see here at the bottom. The first number is always feet. The second number is always the inches. And the third number is 1/16 of an inch. This nomenclature was adopted by the truss industry to allow for easier digitization of designs and to ease calculations. Now, while the first and second numbers are pretty straightforward, typically you will see the third number listed in multiples of 4. Again, not always, but is listed in 4s. A 4 means then 1/4 of an inch, 4/16. 8 means a 1/2 inch. 12 means 3/4 of an inch. Now, that isn't to say that you won't see odd numbers. You'll see them quite often. And then those will just be read as 1/16. Again, the reason for this approach is to allow for quick calculations without requiring the use of decimal points or complicated fractions. Now, while each proprietary design software may display truss dimension information in slightly different ways, there are a few key pieces of information to always look for. The first is the overall truss span from outside bearing to outside bearing. Another key measurement is the length of each truss panel, meaning the distance between the center of one joint and the center of the next. And I'll talk a little bit about the joints in a minute. Now, this information is typically displayed on the truss design drawing from left to right. Again, you'll usually see this information displayed at both the top and the bottom of the truss. But again, this information will vary slightly because the panel point distances at the top of the truss will typically be very different than the panel point distances listed at the bottom of the truss. As you can see on the screen, this is a very complex truss design, and so there are several panel points that are identified. But as you can track from left to right, the overall length will be the same of the truss. It's just the panel lengths that vary as you go from left to right. All of this information is critical when trying to locate or identify an issue with a truss and communicate with the truss designer or truss manufacturer about that issue. On the left and right side of the truss design, you'll typically see 2 or sometimes even more measurements. The main measurement is the overall truss height from the peak of the truss to the bottom of the bottom chord at the bearing. Now, in some instances, this can help quickly determine or verify the overall height of the structure, for instance, but you do need to be careful because for complex trusses like the one on the screen, you end up having bearing heights that are not equal. And so when that occurs, you can end up with multiple measurements on one or both sides of the truss. So in this case, the height of the truss from the lowest bearing point to the peak, or the highest point of the truss, is 10 foot, 11 1/4 inches. In some instances, this measurement will be different than the overall truss height. In cases, for example, where the top chord may extend below the bottom chord to create an overhang condition, or tail, as an example, the extended top chord will increase the overall truss height. And this will be noted in the measurements at the left and the right. This extended top chord overhang lengths, or tails, will, of course, be called out in these instances. With the truss on the screen, those overhangs don't extend below the bottom chord, so they're not noted. Now, another measurement that you will typically see in the areas on the left and on the right are the heel heights. The heel height is the vertical distance between the bottom of the truss at the bearing and the top of the truss top chord. Now, in some cases, this can simply be the height of the top chord itself, typically with an angle cut, if the top chord is essentially the end or heel of the truss. And then you don't have an overhang as well. But in other cases, like you see here on the screen, where the heel is raised, this measurement can, of course, vary quite widely. This is an area where, in talking to component manufacturers, building designers can really help with accurate truss design. They can do this by calling out the desired wall heights and roof diaphragm heights. By doing so, truss designers can ensure that heel heights remain consistent even as different roof planes come together in a system. As you look at trusses like those on the screen, you can imagine that as the truss profiles change from truss design to truss design, and then the elevations change, sometimes it can be difficult to ensure that all of the trusses have, for example, the same roof diaphragm height, which would be a real problem in the field if they aren't, right? The roof sheathing won't go on correctly. So again, building designers can help by specifying what they desire to have happen out on their plans. Now, I just mentioned this earlier with regard to truss length and truss height, But the truss design drawing will also show where the bearing locations of the trusses are located. Often, trusses are designed to provide a clear span between two exterior walls, but that isn't always the case. So it's important to look for the bearing locations on the truss design drawing. In the case of this truss design, there are two exterior bearing locations, as you can see here. But there's also a third around the midpoint of the truss. When this happens, the truss design drawing will break the truss dimensions up and give you two separate dimensions, basically the spans between the bearing locations. So sometimes if you're looking at a truss design drawing and it's not exactly clear whether or not something is intended to be a bearing or not, the truss dimension at the bottom will provide a clue as to whether or not there is an intended interior bearing. Again, when you see this, as you compare it to the measurements below, it will not call out the overall length of the truss. That overall length of the truss will be in the information below the individual spans. Now, the truss design drawing will also call out the pitch of the truss top chords. So you can see them here. The first number indicates in inches the rise of that truss over 12 inches of run. So I'll point that out again. The first number in the pitch will always change. It will be a different number depending on what the pitch is. But the 12 inches of run is standardized across the truss industry. And so that number will always remain the same. Anytime you're talking about a truss pitch or looking at a truss design drawing, it will list the pitch by the rise over the 12 inches of run. The higher the number, of course, the steeper the pitch. Inversely, the smaller the number, the flatter the pitch of the truss. On this truss design drawing, you see what looks like maybe an old division symbol, where you have the 6.00 and then the 12 within the box. It's quite common in other truss design softwares to output this number and showing essentially a triangle to designate what the pitch is. Now, each truss has a few key elements to it. There are the top chords of the truss, and then there are the bottom chords. These make up the perimeter of the truss. This perimeter shape, again, is typically dictated by the architectural plans. They give you the length, the size, the height, all those kinds of things. Along the top of the top chord is the upper perimeter of the truss. This is typically where sheathing or purlins are applied in the field, creating the roof diaphragm. And the bottom of the bottom chord is in turn the lower perimeter of the truss. And this is typically where gypsum would be applied, or what is typically referred to as the ceiling diaphragm. Now, the remaining wood members are called webs. And the webs layout is determined by the truss designer using alternating members in compression and tension. And again, I mentioned this early on, the truss designer and component manufacturer has a great deal of latitude then in determining how these webs are spaced throughout the inside perimeter of the truss. And that really is, what the magic of the truss itself. Again, putting these members into compression and tension to adequately transfer load from the peak of the truss down through the exterior bearings. Now, in every location where a web member intersects with a cord, or a cord intersects with another cord or is spliced, there is what's called a truss joint. Now, each joint is made up of these wood members, whether they're bottom chord or a top chord and a web. they're all held together with a metal connector plate. And again, as I talked about, this industry really started in the 1950s when the first metal connector plate was developed that didn't require additional fasteners. These metal connector plates work by essentially embedding several teeth within the plate into the wood members. And I'll talk a little bit more about plates and plate sizes here in just a minute. But the last thing I want to point out is that in the truss design drawing, every joint will be numbered. And they typically those numbers will travel around the outside perimeter of the truss, typically starting in the bottom left-hand corner and moving up. So a lot of times you can find how many joints are in a truss by quickly navigating sort of to that bottom left corner of the truss and seeing what the highest number is there. These joint numbers, again, are another easy way to identify a location on a truss in case there's a question or an issue. These joint numbers are also referenced heavily in the information below. Again, we'll go into that in part 2 of this presentation. The size of each metal connector plate will be called out on the truss design drawing. For instance, if it states 3 by 10, the plate is 3 inches in height by 10 inches in length. These sizes are the minimum sizes required in order for the truss to perform as designed in the truss design drawing. That said, manufacturers do have latitude to use a larger plate on a joint than what is specified in the truss design drawing. The motivations for that is commonly called in the industry, the motivations for what is commonly called in the industry as upsizing plates varies widely. There are too many motivations to sort of really get into, but like one instance has to do with the interaction of the connector plate with the lumber used in the truss. And again, I'm leaving this truss up here to provide an example. So if you look at this joint up here that's in the red box, there are several members and 2 different top cords that all run into this one joint. Now, each joint in a truss has a minimum number of individual teeth from a connector plate that must fully embed into each wood member in a given joint. So when you look at this, that's a lot of precision that's required to place that connector plate exactly so that there is the required number of embedded teeth into each one of those wood members. Many truss manufacturers do this just fine, it's not an issue. But sometimes a manufacturer may want to not have to worry about perfect placement, and I'm talking about exact placement of the plate, or they may not want to worry about potential lumber defects like wane, where you don't have perfectly smooth and square edges to the wood, and so there may be wane in that joint for a particular wood member, and so that might impact the number of teeth that can be embedded into the wood. So if a manufacturer doesn't want to worry about that, they may choose to upsize the plate to ensure, again, they reach that minimum threshold for the number of embedded teeth in any given wood member. Quickly, maybe another example is if a manufacturer may limit the number of different sizes of connector plates that they keep in stock at any given time. Some component manufacturers have a majority of their book of business based on a certain type of construction, whether it's small single family or large agricultural. And because a majority of the product they put out uses the same size plates within a certain spectrum, they may not keep in stock some unusually sized plates. But when the truss designer is designing a particular truss, sometimes a smaller truss size may or may not work, or it may work. So, for example, they may have a truss that designed where a 3 by 5 plate would work just fine, but they only have 3 by 6 plates in stock. Again, 3 inches high by 5 inches versus 6 inches wide. And so they may decide to just put 3x6 plates on it, move on. The only time that might be an issue, it's not really an issue, but during a field inspection, a building official may notice that the plates are a different size than what's called on the TDD. But as long as the plates are a larger size, this is completely acceptable. Now, the truss design drawing will also indicate the orientation of the truss plates themselves. Again, different proprietary design software packages will show this a bit differently. But this one on the screen will show the orientation as two parallel lines. So this first one, you can see they're up and down, from top to bottom. This one, you can see that they're angled with the top chord of the truss. And the one at the top, of course, it goes straight across, same as the one at the bottom of the screen. I should say that, as you can also see on this truss design drawing, very often the plates will also be graphically shown on the truss image themselves. So between the truss image and, again, this additional sort of marker, the orientation of the truss is typically pretty easy to be able to pick out. But sometimes a plate's orientation will also be noted below on the truss design drawing. Again, we'll address that later in part 2 of this presentation when we get into that portion of the truss design drawing. Now, again, trusses are designed as essentially two-dimensional framing elements. Their ability to resist loads is maximized within the plane of the truss, from the top chords down through the bearing locations. Yet, each truss element works within a three-dimensional roof or floor system. And while the truss design drawing concerns itself mainly with the elements of the two-dimensional truss, it does incorporate an important three-dimensional element in the form of truss member restraint and bracing. As you can see on the screen, this is an image from BCSI, and it essentially shows web member bracing. So SBCA publishes this document entitled the Building Component Safety Information Guide, the BCSI. BCSI contains the industry's best practices on a wide range of topics that pertain to handling, installing, restraining, and bracing of all structural building components, including trusses. And there are two significant portions of BCSI that are dedicated to truss bracing. There's one section that's dedicated to temporary bracing, and then another that's dedicated to permanent bracing. Temporary bracing is bracing that is installed during the installation process, but then is typically removed, although it doesn't need to be, if it's in the web member plane. And then there's permanent bracing, which is intended to be installed and remain in the system in perpetuity. And it's that second part, the permanent bracing, that will often be called out on the truss design drawing. So, as I mentioned, trusses perform well within their lateral plane, but sometimes the forces designed to go through a web or cord in compression, so in this instance, let's say these two webs, these webs, when in compression, could cause the truss members to buckle out of plane. This could potentially cause significant performance issues. So, in order to resist that permanent buckling, permanent restraints and web reinforcement will be called out on the truss design drawing. So you'll see them located here and here. Installing this bracing will allow the compression forces going through those two web members to be distributed between multiple adjacent trusses in the system. Again, this is sort of an interplay between the two-dimensional truss design drawing, the individual structural framing element that is a singular truss. And again, some of what may be required for the function within the overall roof system. I didn't have a truss design drawing showing this, but sometimes you will also see web reinforcement also called out similar to this on the truss design drawings. And that will typically show a 2x4, 2x6 member affixed to one of these webs along its length. And sometimes you just need one, and that would be called, for instance, a T-brace because of the shape or the letter it makes with its shape. Sometimes it's a U-brace. You can guess what that looks like. So sometimes that web member restraint is added as well. Another important aspect of these horizontal restraints called out in the truss design drawings are the diagonal braces that need to be included. As you look at the image on the screen, those diagonal braces are the red members. Now, the truss design drawings won't call out the diagonal bracing on the individual truss design drawings. It's going to be up to the installers to decide where to install these diagonal braces. Fortunately, BCSI, again, provides guidance to installers on how this needs to be handled in the field. That's where I'm going to end our exploration of the graphical section of the truss design drawings. Again, in part 2 of this presentation, we'll walk through the data contained in the lower portion of the truss design drawings and talk about what building designers should pay close attention to during their review. To end this presentation, I just want to talk briefly about current trends towards offsite construction and leave you with an argument for why it behooves building designers to take proactive steps towards collaborating with today's component manufacturer and better understand how to specify roof trusses, wall panels, and floor trusses in their future projects. Now, offsite construction, which includes component manufacturers, didn't become, a sexy jargon overnight. Home builders across the country have been trying to ramp up production since, I would say around 2012. It's been pretty steady growth when you look historically over that time period, over the last, 12-ish years. The lesson they learned, though, over that time period is that while traditionally they could throw labor at the problem of how do we ramp up home production quickly, labor just has not come back since the last downturn, like it did in past cycles. And so builders have really begun to focus more on how do we solve this problem? How do we meet the current demand, which you talk to any economist, they make it very clear that there are a lot of people wanting to buy houses that currently can't get them. That we need drastically more housing stock than we currently have available. So the demand is there. The question is how can today's home builder effectively ramp up production when they don't have job site labor to throw at it? Well, the obvious solution that they've sort of arrived at is they have to look offsite. The interesting thing is, I mentioned that 12-year time period. That's a long time for there to be steady, continual growth in the housing industry. Because that's happened, there's really been a concerted focus and a lot of capital investment and research and development in the component manufacturing space to make improvements to production quality and capacity in order to meet this growing demand for offsite construction. And this shift is, profound because the offsite component manufacturer can do the design and manufacturing process much more quickly, much more efficiently, and with much better precision than what could ever have been done in the field in the past. And we've seen that really ramp up just in the last 3 to 5 years, where we've seen, considerable investment in everything from equipment to software. We spent a lot of time in this presentation sort of talking about the software side of things, but the manufacturing process has also taken, very large steps towards greater automation, whether that's automation in material handling, whether it's automation in cutting through linear saws that can batch trusses to perfectly fit sort of what's being erected in the field. There's automated jigging systems that allow component manufacturers to quickly switch from truss profile to truss profile. That automated jigging system gives component manufacturers added incentive to look even at more creative ways to arrange those web patterns within the truss to provide an efficient and effective framing solution, one truss at a time. Back when all of the jigging for a production table was done by hand, there was the incentive for the manufacturer to try to make as few different truss profiles as possible to get the job done. But with automated jigging, and again, linear saws and automated material handling, and even laser guided systems, that incentive to find solutions that use less material or lower grade material, but still provide a superior structural framing product has increased very rapidly. So again, when you look at, this picture on the right shows you sort of the current state of things for the home builder as far as their ability to find job site labor to stick frame or install framing products in the field. You really see a builder or a developer really motivated to try to figure out how to incorporate more of these off-site solutions. So for building designers, it really behooves them to sort of take a serious look at this industry, its products and services, figure out how to better specify them in their projects. I'm going to end with just a few observations along those lines. The truss design process primarily concerns itself with, again, the development of two-dimensional structural framing elements within a three-dimensional roof or floor system. So the building designer, again, dictates the overall shape, determines they determine the paths that the loads will flow through the structure from the peak down to the foundation. The truss design drawings, though, graphically illustrate each truss for building designers and building officials to make it easier for them to review the individual trusses in a review process. And as you got a glimpse of the truss design drawing examples in today's presentation, again, that truss designer can be very creative in determining exactly how loads are transferred through a truss. If there's one thing that you take away from this presentation, it should be that the proprietary design software that today's component manufacturer has at their fingertips is incredibly powerful. And it gives component manufacturers the ability to offer a wide variety of solutions to really any framing problem that a building designer may face. And this means that the component manufacturer has the opportunity to help the building designer save money and materials, reduce construction cycle times, and reduce waste. All things that, again, the builder today is really striving to find. So the key for the building designer is to find and work with a component manufacturer and explore together the wide range of possibilities that exist and find solutions that work for the next project in their design process. I want to thank you for attending today's webinar. Again, I would love your feedback on how we can improve this presentation for building designer audiences in the field. I found that asking questions in this format can be very difficult, but I've had some great follow-up conversations with people over the last few months. If you have any questions, you have any comments, you have some feedback, you will get an email at the conclusion of this webinar that will have a short survey. Please fill out that survey, give us some feedback. But you can also shoot me an email directly. My email is on the screen. I'll be happy to give you a call and have a conversation about anything that was brought up today and any suggestions you might have for part 2 of this series. Again, thank you and have a good day.